In this lecture, we'll discuss the problems and the solutions of the final exam of this semester. And the final exam consists of 5 problems. Problems number 1 is shown here, and this problem deals with the Cauchy's and Nyquist theorem applied to the stability analysis of some system. Shown below is the loop gain plot of a conceptual systems. As I said in the class, this kind of situation won't happen, but this problem will be a good example to illustrate the concept of Cauchy theorem and the Nyquist theorem. The problem is listed below. There are two sub-problems. Problem number 1 is for the system A, assume the loop gain LS has one right-hand plane 0 and answer the questions. Question number 1, number 2, number 3. And as I said, as I written in the problem, this has the loop gain has one right-hand plane RHP 0. So for the Cauchy's theorem is related with the determining the RHP 0 or pole of a rational function of S-plane LS. So we are dealing with LS, and the reference point is here, and the equation we will using is this one. NO is N stands for the origin of this system, and you draw the line here, then the crossing point is 1. Okay, so in this situation, N0 and O, Cauchy's theorem applied to the origin is 1. This is the number of encirclement of this origin, and the G is RHP 0 contained in loop gain, which is 1, and we want to know the P, number of P. Okay, so using this equation, N0 is G minus P, and it translates to 1 is 1 minus P, so P is 0. So that means there is no right plane pole in LS. So next, so there is a solution of this problem, and problem 2 is use the Nyquist stability criterion to judge stability of the system. So I use the notation -1, referring to we are concerning with this critical point, and the equation remains the same. The problem here is we need to determine this, and P is determined in the previous problem, and N-1 should be determined based on this loop gain plot, this polar plot. Okay, then this is a critical point, and you you draw a line segment, then this is one encirclement, and this is another encirclement. That does not mean there are two encirclements, but because this direction is opposite, effective encirclement is 0. For this case, this N-1 is 0, and this is given by Nyquist criterion, same as the Cauchy theorem when that theorem is applied to this point. So G minus P. Okay, and we know P in the previous problem. So this is 0 and P is 0. That means G is 0. This means there is no RHP loop in characteristic equation of 1 plus LS equals 0. Okay, so the system is stable, but you should be careful and determining stability. It has this line segment. This line segment indicates the phase of the loop gain smaller than -80 with its magnitude larger than unity. This is the unit circle, and anything outside of this means the magnitude of the loop gain is larger than unity, and with that the phase is less than -180 degree. That is determined conditionally stable system. So this system is conditionally stable system, and usually, not usually, but always conditionally stable system becomes unstable when loop gain, magnitude of loop gain is reduced. So take a look at this line segment. If the loop gain magnitude is reduced, this line segment will be something like this, encircling this critical point. Then means the system becomes unstable. That is the definition of conditionally stable system. So we solve this and this, okay? And the magnitude of this loop gain is decreased by factor of this one, and this one, okay? So take a look at this. This point is minus 4, 0. If the magnitude of the loop gain is decreased by factor of 1/4, then this point will pass this. Okay, what I mean is, if that happens, this loop gain plot will be something like this. Okay, let me use this one. Let me use this color. That means this one will be something like this. So it passes this critical point, minus and 0. That means this I wrote down here, when decreased by 1/4. In terms of its magnitude, the system is marginally stable. If it reduces further, then this will go down like this. Then it becomes unstable. And if that reduction ratio is this one, okay, then this reduction ratio is smaller than this. That means the gain is larger than this case. Then this will be something like this. Okay, so this is a borderline. So when this reduction rate is this number, the system is on the borderline of stability and non-stability, and called the system is marginally stable. And this ratio, this incremental ratio is this one. The gain is reduced too much and the system becomes unstable, and before this system remains stable. So this is the conclusion of the previous discussion. So you need to draw the response of this system, typically response of those three systems that is shown in the next page. And that finishes problem number 1, and the problem number 2 is very similar to the problems number 1. So that, but difference is here, is this small region is different from the previous case of this. Okay, this is also conditionally stable system. If the gain is reduced very much, then this part will be something like that. Okay, and also no, not this one. This part will be something similar to this type of shape, this type of trajectory, and the system becomes unstable. So system is also conditionally stable system, and you need to pay attention to this dark black rectangle. Okay, if the gain is increased 4 times, now this coordinate of this point is this number. Okay, if this one is increased 4 times, then this will move to this. Okay, so for this case, the system becomes unstable when gain is reduced, and it also becomes unstable when gain is increased. Okay, because of this part. So this part is a little bit different from the previous case. When gain is increased by 4 times, this part will move this. Okay, so this is the borderline of that case, which makes the system marginally stable. If the gain is increased beyond that point, for point 1, system becomes unstable, and the gain is reduced below this critical point, critical number, system remains stable, right? So this case is a little bit different, and again, this is not practical case, but I prepared this problem to help you to understand the concept and content of this Cauchy's theorem and the Nyquist theorem. Okay, of course, by drawing some line, for example, like this, and you can confirm this trajectory does not encircle critical point and system is stable. Okay, and again, if you plot this is not encircled by this trajectory, the system is stable. Okay, but because of this part and this part, system is defined as conditionally stable, and because of this system can become unstable when this gain is decreased and also gain is increased due to this part. Okay, so most of your answers is not fully explaining the nature of this problem, but most of your answer is correct, and the waveforms of those cases are shown here. This is, of course, this is the unstable case, and this is a marginally stable case, and this is a stable case, this is a marginally stable case, and this is unstable case, and so on. Okay, for this case, this is stable and this is marginally stable. This is unstable because this trajectory encircles this trajectory encircles this critical point, and this trajectory does not encircle this critical point. But nature of this figure, so that will happen when gain is reduced, the problem occurs. Because of this, the problem will occur when gain is increased. Okay, so I hope this help you to understand the nature of this Cauchy's theorem and the Nyquist stability criterion. Okay. There is a much easier way of understanding this, and in the future I will cover that in the different courses. Also, there are many way of understanding this, but the discussion, technical discussions covered in the text in the class is the very original and very theoretical method, and other things is some simplified method. Some simplified method is still okay in practice, because this strange behavior, these strange cases won't happen in practice. Right? So this is about the problem number 1, and the problem number 2. We have this diagram. This is the schematic of DC motor drive system, and we have this feedback compensation and the difference amplifier, and this is the input command signal, and here is you have 6 volt input, and this 6 volt input is divided by 3 identical resistance. So when this switch A, SA, is placed at a position, this voltage becomes 2 volt, and when this switch is placed at this B point, this voltage becomes 4. Okay, so by changing this switching position, the input voltage can change from 2 to 4 or vice versa. Okay, and this is a differential amplifier, and this is a compensation. Okay, and first problem is expressions of compensation shown in the circuit and the functional diagram. Very easy problem. So we discussed this a lot in the class. This create a zero. Okay, and the combination of this resistor and this capacitor create the integration function, and integration, so this transfer, this is connect closed. Okay, initially we assume this SB closed, so this is SB was open, so it's not existing. Then this is what? This is just sign changer. Okay, so just it produced just -1 gain. Okay, so sign of signal is just inverted, and then compensation is this one. So it has structure of integration, and it has 1 0 here. Okay, and integration gain is determined by this one and this one, and the location of the zero frequency is determined by this capacitor and the resistor, and they are determined like this. Okay, so transfer function is this one. GCS is given by this, and the KC is this number, and omega G is 40. Okay, so that take care of this problem number 1, and problem number 2. Sketch the asymptotic plot for the loop gain magnitude and the loop gain plot, and specify all the important information, which is very simple. Right? Because we already know this compensation structure. This is compensation, and this transfer function is given here. So it has 1 block, it has another block. Okay, and the disturbance is coming in between. So this is cancelled. Okay, so we have one integration and one pole. Okay, and this 0 dB crossover frequency of this integration gain and pole frequency occurs at the same point. So the plot is very simple. So okay, let me repeat this. This is a GCS expression. We found out this. This is a GCS integration and 1 0. Okay, and loop gain expression is this one. Loop gain expression is we only take this part, and this part. Okay, integration and pole at 4,000 because they are cancelled. This is a pole zero cancellation. So -1 slope. Loop gain is declining with -1 slope. This is -1 slope. And this is the 0 dB crossover frequency. At this frequency, it has one pole at the same frequency. The slope has been changed from -1 to -2 at this frequency. Okay, the slope becomes -2. This loop gain crossover frequency is 4,000. Phase is this one at this frequency. This is just single pole, but it changes from -1 to -2. So single pole has this -45 degree for decade slope, and it starts from the -90 and ends at -180 at this frequency. The phase is just -45 degree, and obviously phase margin is 45 degree, and at this frequency it will show some peaking. Okay, that peaking will occur everywhere, and the magnitude of the peaking is determined like this. Okay, so actually, to be exact, this will be some peaking, something like this. This is very small peaking. This is a small peaking. Right. So let me use this one. Let me change color to purple. So something like this, and this is 20.3 dB peaking is occurring at this frequency. Okay, and problem number 2 is this one. All right, sketch the asymptote plot. Sketch the asymptote plot of this loop gain, magnitude and gain. Okay. We already finished that. And the problem number 3 is consider the input-output characteristic of the converter, and sketch the transfer function, magnitude, input-output transfer function, magnitude and phase. Show all the important features of the plot, peak magnitude and corner frequencies. And problem number 2 is this SA is changed as shown here. So for this, until this value, this is 2 volt. Onto this point is 2 volt, and this is 4 volt. Okay, and this becomes, again, it becomes 2 volt, and the transition time occurs here. Okay, so this is the graphical illustration of the switching action of this SA. Okay, for that case, as I said, until the crossover frequency of the loop gain, input-output transfer function, magnitude is 0. Okay, and after this, it follows this loop gain plot. So this shows this typical low frequency characteristic system, and this is called equivalent second order system characteristics. We went through this many times. So it starts from this 0 dB here. It shows 2.3 peaking at this frequency, downpour frequency, and the slope is changing to -2, and the phase at this point is -90 degree, and finally it terminates at this -180 degree. Okay, and sketch this. So to sketch the step input response, you need to find out zeta, and this is the relationship between phase margin PM and damping ratio zeta. And using this number, using this equation, you conclude this, and omega n is this double pulse frequency, which is 4,000, and this formula is given. This is the maximum peak factor is 1.37, and then the peak value. This is not frequency. This is omega s is the rotational speed. Maximum value is this is the peaking, okay, and this is the initial value. So those by summing these two numbers, this is the maximum value of this peak value of this omega st, and this settling time 5%. Bound settling time is 3 times this one, and this number is 2 millisecond. Okay, so this is the accurate prediction of this, and after this, and it reduces by 4, so it goes down to this is 4, okay, and this is 2, and there is some undershoot across here by factor of this one. So the change is this one. So originally it was this number, and the maximum transition is this number. So by subtracting them, so final value of this low minimum value of this speed is this number, and it returns to this original value of 2 radian per sec. All right. So this is it. So problem number 1, 2, 3. Okay, there is no major point to discuss. And problem number 4 and 5. So problem 4 is to address the input to output characteristic of the system. Okay, and it has sub problems. Sketch input to output transfer function. This one, and with VIN is 0. Okay, VIN is 0 means what? This input command is 0. Okay, so response alone this, okay, and alone the disturbance source, and sketch the asymptotic plot for disturbance source, magnitude of them, and show magnitude of it, and show the all the important features of plot, such as peak, magnitude, and corner frequencies. Right. So this is 0 dB line, and this is the loop gain plot. Okay. So it has -2 slope, and this is input disturbance to load current, the output transfer function. And before this frequency, we have subtraction rule, and by subtracting this, and this magnitude becomes the same, and this becomes the same, and so on. As I said in the class, and this should be symmetric, and this triangle and this triangle, they are symmetric. So this line segment is looking at this point. So equation of this is this one. This start with differentiation, and the differentiation gain is this number, and it has first pole here, and it has another pole here. Okay, so this is asymptotic plot, but we know the phase of this is 45, so it has this some very small peaking. So some very small peaking. The dynamics of due to this peaking will be minor. Okay, it is not fully second order system. It has, because there are 2 poles, so it will consist of 2 exponential terms, and plus some oscillatory function, all caused by this peaking. Right. So first ignore this. You can ignore this, and without considering this peaking, you have this equation, and take inverse Laplace transformation of this, and by expanding this in using the partial fraction expansion method, and taking the inverse Laplace transformation, we have this expression, and our response is consists of 2 terms, this terms and this terms, and one has positive coefficient, and the other one has the negative coefficient. So we have this shape and this shape. Okay, and some of them is shown here. Let me use this one. Some of them is shown here, and it will show some oscillatory behavior, very little tint of oscillation. Okay, let me use this. Okay, then it will show. Okay, something similar to this. All right, so this is answer. Okay, but you may disregard this small oscillation shown here, all right? So small oscillation will be ignored, okay? But drawing something similar to this is wrong. Some student, they plot this. This is not right, okay? I don't know where this comes from. Right? And the last problem is that was number 1, and number 2 is dt is given by this, okay? And still you have input, all right? Because we have this is connected this A with at A position, you have input signal. So input signal will generate this 2, all right? And the response due to this torque disturbance is here. But according to this transfer function, we know that the gain at the DC is 0. So this term is totally stopped. And at this point, at this frequency, this is 400 radian per sec. The gain of this is minus 20 degree. Input is 4. So result will be 0.04. Okay. And sine 400t phase of this flat part is what? Phase is 0. Okay. And at this frequency, 4 times 10 to 4 frequency, the gain is minus 60 dB. So this is the input, and the magnitude will be this one, and the phase is this slope is declining minus 1. So the phase will be minus 90 degree or something like that. Okay. Of course, this is approximation, but very good approximation. So this is the correct answer. May few students find out the exact answer. Because of this, many of you write down these 2 terms correctly, but some students use number 4. That was not correct, right? Only 2 is coming from the input, right? And the problem number 5 is this switch is closed. This switch is closed. If a switch is closed, and this will generate, this is the parallel connection of C and R will create the pole, right? Because this pole across this part, this pole becomes real pole. So in terms of the loop gain plot will be modified something like this. Oh, what happened here? Okay, let me move this. No. Okay, I'll fix this later. Somehow something happened. All right. So magnitude curve still start with minus 1 slope here, but it originally, this is the integrator gain. So, and this is the original one, and we have only additional pole at this frequency, and so slope becomes minus 3, and it is considered as a double pole, and so frequency here is minus 90 degree, and at this frequency, and you have additional 90 degree phase delay, and the phase is minus 180 degree at this frequency. Okay, so with this situation, let me use this. Alright, because this initial minus 1 slope plus additional minus 90 phase delay. So phase is this is the marginally stable system, and the marginally stable system will create increasing oscillation. So that is shown here, and the explanation about that is shown here, is written here. Okay, so we have additional pole at this point. So magnitude becomes 0 at this frequency with the phase of the 180 degree. So it will generate the sustained oscillation at the frequency of this. Okay, and so this start oscillation, and it grows up, and it will settle down with some final value, because the output is limited by the value of this OPM, bias voltage of the OPM. So maybe one example is 4 and 0. Okay, but in practice there is some voltage drop in the internal transistor or BJT. Okay, but you should show this saturation anyway. All right, and the oscillation frequency is 4,000. It comes from this number, and then number is 1.57 millisecond. Okay, so that's number 2. All right, so let's move number 3. I'll be very careful not to move around this. Okay, problem number 2 considers this diagram. Right, so it has the same situation. So this is a plane. This plane, and which has this sign inversion block, and this is what? This is compensation. This is compensation, and this is difference amplifier. Okay, so problem number 1 is modify the feedback circuit that contains the minimum number of this OPM. Minimum number is 1, right? 1. Okay, we need only one OPM, which is this. All of these can be combined into one OPM. This one, this one, this one, and compensation is here. Okay, and this negative feedback is here, and because of we have minus sign, this additional sign changer is not necessary. Okay, it should be avoided. So this is the correct answer. Okay, I think I explained this several times, and I gave several examples for this. So in practice, you don't use this. You don't want to use this, right? The same function can be achieved by using this simplified circuit, having only one operational amplifier, right? And you are asked to design feedback compensation with the following loop gain specifications, which is 0 dB crossover frequency is at this frequency, 45 degree phase margin, minus 20 dB decade slope for the frequency below this crossover frequency, and use the simplest GCS structure. Okay, so use the simplest GCS structure, which is this one. Okay, and this one, and then loop gain transfer function is this. This comes from the plant, and this is this transfer function of this feedback compensation. So it has a feedback structure and containing generated by these two capacitors and the resistors. So omega m is 200. Okay, because we have 20 already, so if you put 200 here, you will get this number, right? And you want to cancel this and this, this and this means, so this omega p should occur this 400, and omega g should occur at this frequency. Okay, so omega n integrator gate is this number, omega g is this number, omega p is this number. Okay, this is a pole. You know this combination of this will generate 0, and the combination of these 3 elements will generate 0, right? So, but if this is true, if C2 is much larger than this is true. If you if you evaluate this is this one, and this is this one, and the parallel combination of this is just C3. So you don't use C2 here. Okay, this is the simplified approach. Perform task in the simplest way is if you have two capacitors series connected in series, and one is much larger than one is much smaller than the other one, you take just the smaller one. So you just take this. Okay, so integration gain is given by this 200, and this R1 is given in the problem. So you determine this, then you determine this using this equation, and this, and using this equation you determine this, right? Actually this is the C3 in series with C2, but C2 is much larger than C3. You just ignore C2 and you simplify your calculation. So that is the answer. All right. Okay. That is the answer. This is a simple problem. Now you are expert in this. Okay. Figuring out the transfer function of this and determining these values for the given cone frequencies. That is very easy, right? So this can be modified, or 3-pole 2-0 compensation. This is actually 2-pole 1-0 compensation. Okay. And problem number 3 is determine this one. Relocate the loop gain crossover frequency at this frequency by changing the values of the circuit components or value of the circuit component. That means you can change one component, or you can change one and more component, 2 components or more. Okay, but I specified this keeping the phase characteristics unchanged, and simplify your design and perform your task in simplest way. It just increases the gain of integrate the gain twice without changing only one circuit component. Okay, so you can change this 3, but you don't have to do that. Okay, just change this one. Right. So then corner frequency will remain the same. Only integration gain will be reduced by factor of the 2. So use R1 2k ohm instead of R1 of 1k ohm. Then omega m was previously 200. Now omega m becomes just 100, and the modified gain is this one. Okay, previously the loop gain was something like this. Okay, then you just reduce this, then until this, then maybe this will be something like this. This is a modified plot of the loop gain, but this part you don't worry about this. So before this loop gain crossover frequency, it follows this, and after that it follows this. Okay, this, so there is a one slope change. There is no peaking here, and there is another slope change here. Is coming from this open loop disturbance torque to output transfer function. So now the input to output transfer function looks like this. So it is like this. Okay, so it consists of 2 exponential terms, and this occurs at low frequency. The speed of the input response is modified. It becomes slower than previous one. Obviously, it becomes slower than previous one, and shows some response consisting of 2 exponential terms only. Okay, so this wording is not good. Okay, it becomes the second order system. Characteristics will be disappear, and it consists of 2 exponential terms. One is coming from this, and the other is coming from this, and the characteristic is very similar to the previous one. Okay, but it consists of only two first order terms, which is way different from the previous case. Right? And problem number 4 is this one. So this is the conceptual loop gain characteristics. We have magnitude plot over here and the phase plot over here. Okay, at the 0 dB crossover loop gain frequency, the phase margin of this system will be determined. Phase margin will be determined like this. This is 180-degree line. So this is 20 dB. So PM is obviously 20 dB, which is this. Okay, and this is the frequency at which the phase of the loop gain drops to 180 degree. At this point, we define the gain margin. Gain margin is difference between gain at this frequency and this 0 dB line is gain margin, which is very small. It has only gain margin of 30 dB, and before this, this will show some peaking here because of this phase margin, and the peaking is this one. This is the magnitude of the peaking, is 9.2 dB. All the students provide correct answer for this, but this one, very few students, they answered correctly. Okay, let me explain this. All right, so at this point, this when gain margin is determined, the phase of the magnitude is out of phase with respect to this. Okay, this is unit vector starting from origin to 1. Okay, this one, and it has minus 180-degree change out of phase, and the magnitude of this is this. All right, then magnitude of by subtracting this, and magnitude of the loop gain is determined by this 1 minus this. Okay, and actually the open loop 20 magnitude is, this is the open loop magnitude divided by this one. Okay, so this is the size of the peaking, and by calculating this, and this is determined as 10.7. So 10.7, if there is some open loop transfer function, maybe something like this, it shows peaking, and it shows another peaking here, and this peaking is larger than previous one. Okay, so usually we worry about this peaking from the phase margin, because this gain margin is much larger than this number. This is some special case. In some special case, this small phase margin will really occur. Okay, but usually this loop gain is declining something like this, and this gain margin will be very large, and this peaking can be ignored. That is the usual case. But somehow your loop gain shape is something similar to this. So it has this, this stays this point for a while, but while the phase is reducing, then this becomes called large peaking. Okay, this will occur when the system has right plane 0, then the 0 behaves as a pole, and that case without changing this magnitude, the phase will drop continuously, then this situation will happen. All right, so this is also important. This is the only one I didn't teach you, but you should figure out this based on the information you obtained during the class. All right, but very few people answered this problem correctly. All right, and the final problem is shown here. This problem shows the loop gain of some system, and it has this feedback compensation, 3420 compensation, but this information is not important here. Anyway, this corner frequency is not important. This information is not important in figuring out the real structure of this. Okay, but it is important to determine the structure of this compensation circuit. Okay, all right. So determine the stability of the system. So to determine stability of the system, take a look at this point, and let me use this. Take a look at this 0 dB line here, and check the phase. Phase is much larger than this minus 180 degree. So you have this much of the phase margin. All right, this much of phase margin. But during this period, this frequency range, this phase is less than minus 180, while this phase, this magnitude is larger than 1. Okay, so this magnitude is larger than 1, and phase drops less than 180 degree. That means if you sketch the polar plot of this loop gain, this unit circle, okay, it starts this 90 degree, it goes like this, and it becomes stable like this. Something similar to this. All right, this is what? This is conditionally stable system. Right? Determine the stability. Be precise in your answer. So the correct answer is conditionally stable system. Conditionally stable is the correct answer, right? And the problem number 2 is first I asked sketch the circuit implementation of this compensation structure without seeing the class note or class slide or textbook. Okay, because you know this, all of this. Okay, you learned this relationship between structure of the circuit component. You can easily draw this because it requires 3 poles. So initially you should have integration. For integration, you need to have capacitors, capacitive path like this. Okay, all right. But you have poles here. This constitutes 0, right? This constitutes a 0. This is a 0. All right. You can add this one. Then this will be another 0. This will be pole, right? Combination of this parallel component will be pole. But then this should have infinity impedance. So this should have only capacitive paths. This is resistive. So capacitor cannot come here. So the only possibility is you have another capacitor here. Okay. Then you have this capacitive path, 2 of them. Right, so this DC current is passing through this, okay, and to have this integration function, you should have at least one this resistive load. So you don't have any resistive load. Suppose this is capacitive, then it is impossible to have integration function. So because of that, this should be resistive. But you need pole and 0 because it requires 2 zeros here. Oh, this one. No. This one. What is this? Okay. This is plus. Oh, no. Okay. I'm sorry. 2 corner frequencies and 2 corner frequencies. So you need two additional corner frequencies. For that, you need a parallel branch here. And if you add this, okay, then you only have one pole. So 1 pole and 1 0, you should include this. And then this resistive and capacitive path will provide you, this is 0, but in feedback amplifier structure, it will be pole, right? And the parallel combination of these two will be the 0. That will be pole. But in this situation, in this inverting amplifier situation, it becomes 0. So 2 poles and 0, a pair of pole and 0 is create this, and another pair of pole and 0 is create at this, and you have this structure of integration. Structure of integration is implemented with this 3 component, and you know this. So this is determined, this 0 is determined by these numbers, and this is a series parallel combination of this. Okay, you know how to do this, and you know how to do this. All right. So you know everything about this structure, and this approach can be generalized to any type of compensation circuit using this OPM structure, which is the most popular way of implementing this feedback compensation. Right. So this and this covered. Okay. Problem number 1. This one is find the range of find the range of this compensation gain, okay, to make a system unstable. All right. So at this point, you have a 6 dB margin here in magnitude. So if magnitude is decreased by 6 dB, loop gain crossover across like this, then system becomes marginally stable. All right. If reduced further, then the crossover will occur. No. If this is reduced less, then crossover frequency will occur somewhere here. Then system becomes unstable because the phase is lower than -180 degree. Okay, and at this point we have 20 dB difference. So if this is decreased by 20 dB, then crossover will occur here. So it hit this point and system becomes marginally stable. If it reduces further like this, okay, then like this, okay, then crossover occurs here and system becomes unstable because the phase becomes less than 1 minus 180. So this is the ditch here. So loop gain occurs. Loop gain crossover occurs at the ditch frequency if KB is in between this value, okay, larger than this value and smaller than this value, then the the system becomes unstable, okay. And another one is if this gain is increased. This is the one point. If gain is increased by 20 dB, the crossover frequency occurs here, and this is 180. The system becomes marginally stable. Okay, so marginally stable means at this frequency 2 pi times. This should be all right. This might be okay. It can be considered as a radian per sec, all right, and this also considered radian per sec. That is okay, all right. But the idea here is the message from this is if the loop gain is increased by 10 times, then system becomes marginally stable, which is this case is increased by 10 times, and it increased further, system becomes unstable. It increased less than this number, system remains stable. That is the idea. Okay, and this example is very practical. In practice, so for the given loop gain plot, you can evaluate the stability and you can judge the sensitivity of stability. That means you can judge when it becomes unstable, how much I can increase the gain, or you can have some information, the safe range of the gain change if you have the chance, opportunity to change the gain, something like that. All right. So this is much better than just try and error method. So with this information, you can finish your job in a systematic and engineering method, right? So that is the end of this final exam, and I think most of you did okay, all right? Okay, again, I hope you keep this, okay, this class slide, and in the future of your career or your study, you may refer this slide, okay, and this the content of the lecture to solve your problem. This is a very practical problems and very systematic way of dealing with the control problems. Okay. All right. Okay. This is end of this semester. Okay. I hope I see you, not most of you, but large number of you in the next semester too, in other classes. That class will be dealing with the modeling, control, and the design of PWM converter, and the knowledge covered in this class will be referred very much. Okay, so you will have good position to take that course, to be good at that topic that will be dealing with in the next semester. Okay, thank you for your attention and patience for last semester. Okay, thank you.